VAR model. Okay. Okay, you see the slides?
Not yet, hocam. Waiting. Yes. Now
Okay.
it's okay.
Yes,
Okay.
hocam.
Thank you. I'm gonna present you the. Last week we presented the vector error correction, and today I'm going to present you the unrestricted VAR model. I will give you some crucial information and very important antidotes for being able to present and do this on eView for your future research. VAR model, which is vector autoregressive integrated model, comprises multiple time series and is quite useful tool for forecasting. It can be considered an extension of the autoregressive model. VAR model involves multiple independent variables and therefore has more than one equations. Each equation uses as its explanatory variables logs of all the variables and likely a deterministic trend. Time series models for VAR are usually based on applying VAR to stationary series with first difference to original series, and because of that, there are always a possible loss of information about the relationship among the integrated series. The VAR model differentiating these series to make them stationary is one solution, but at the cost of ignoring possible important long-run relationship between the levels. A better solution is to test whether the levels regressions are trustworthy. The VAR model usually approach is to use the Johansen's method for testing whether or not the co-integration exists. If the answer is yes, then the vector error correction model is going to be employed, which combines levels and differences can be estimated instead of a VAR in levels. So we shall check if VECM or vector error correction model is being able to outperform VAR for the series we have. The differences between the VAR and VECM, if it is in the question, then through VECM we can interpret the long-term and short-term equations. We need to determine the number of co-integrating relationship. The advantage of the VECM over VAR is that the resulting VAR from VECM representation has more efficient coefficient estimates. And then we are going to the VAR model. The basis of the vector autoregressive model, we lay the foundation for getting started with this crucial multivariate time series model and cover the important details, including what is the VAR model, who is going to be, of course, use this model, and basic types of the VAR models, how to specify the VAR models, and estimation and forecasting for the VAR models will be interpreted. To determine whether VAR model in levels is possible or not, we need to transform VAR model in levels to a vector error correction model in differences with error correction terms to which the Johansen test for co-integration is applied. In other words, we take the following 4 steps. We will construct a vector error correction model in differences with error correction terms, of course, apply the Johansen test to the vector error correction model in differences to find out the number of co-integration. And as you know, none and at most is the subjected. If R, which we are talking about the none or at most, 0 estimate VAR in differences, and R, if it is higher than 0, estimates vector error correction model in differences, or VAR in level, at least one co-integration equation must be exist. Its identification depends on the number of co-integration in the following way. None or so-called 0, R is equal to the 0, then non-co-integration. In this case of the no co-integration, since all variables are non-stationary in level, the above vector error correction model reduced to a VAR model, as I mentioned in the last slide, with growth variables. At most 1, which is R is equal to 1 co-integration vector. At most 2, R is equal to, then 2 co-integration vectors is supposed to be exist, and at most 3, error is 3, then full co-integration is supposed to be subjected. In the case of full co-integration, since all variables are stationary, the above vector error correction model reduces to the VAR model, with level variables. It is also important to determine when we are going to use and how we are going to use VAR or vector error correction. If all variables converted to the first difference, then they become stationary, integrated in the same order. Null hypothesis variables are stationary. Alternative hypothesis variables are non-stationary. If the variables are co-integrated and have non-linear association, then we run restricted VAR, that is vector error correction. In the other case, if the variables are not co-integrated, we cannot run vector error correction. Rather than we use or we run unrestricted VAR, which I'm going to introduce you today. The restricted VAR model, as I have given you in the last lecture, the guideline, after performing co-integration tests, results will show following estimations. The trace statistics is becoming higher than or more than test critical value, which is null, is there is no co-integration, and the alternative, there is co-integration. And when the trace statistic is more than test critical value, we can reject the null hypothesis. There is co-integration. The probability value is supposed to be less than 0.05. In the opposite case, where we are going to the unrestricted VAR, after performing the co-integration test results, will shows following estimations. The trace statistics now become less than the test critical value. The null, there is no co-integration, and the alternative, there is co-integration. And when the trace statistics is less than test critical value, we cannot reject null hypothesis. There is no co-integration, and the probability value is more than 0.05. Then we will then perform unrestricted VAR. The guideline to the VAR, variable selection and the purpose. The initial step is to understand the task and at the end. What kind of variables should be included, what maximum lag order would make sense based on the frequency and description of the data, what is the underlying economic and financial theory that is assumed beforehand. The guideline is going to the first data analysis and the transformations. After selecting the data, the second step will be examine the data, plots and summary statistics, and answer these questions. Are there any outliers in the data? Is there any missing data? Do you need to transform the data? Example, take logarithmics. And do you need to create any new variables? For example, GDP per capita, number of children per households, etc. The unit root test after we are performing is supposed to be the final set of the variables, where we need to test whether they have unit root in the first difference or the second or stationary. To do this, we are using ADF or the other test, and it is expected the probability after performing the first difference becomes more than 0.05, which is suitable for the unrestricted VAR. The VAR model order selection, usually model selection is done based on some kind of information criteria. We are using the Akeke info criteria or Bayesian info criteria, Schwarz Bayesian info criteria. Sometimes other information criteria are going to be used, and this can be done using the VAR selection from the VARs package. This Bayesian info criteria penalize model complexity more heavily. The co-integrating or the unit root series, if the time series has a unit root, we should check whether there are any co-integrating relationship between the series. There are 3 types of tests which can be performed. And then, of course, as I mentioned to you, the maximum eigenvalue and the trace statistics will be performed. The maximum eigenvalue are smaller than the test critical value for the vector autoregressive. And similarly, the trace statistics are also smaller than the test critical value. The opposite case is then the vector error correction is supposed to be realized. The VAR modeling is a multiple step process, and the VAR analysis involves the specifying and estimating the VAR model. using inference to check and revise the model as needed, forecasting and structural analysis. The VAR model, vector autoregressive models, are used for multivariate time series. The structure is that each variable is a linear function of past logs of itself and past logs of the other variables. Who use VAR models? VAR models are traditional, widely used in finance and econometrics, as we are using as an economist, because they offer a framework for accomplishing important modeling goals, including stock and Watson's, data description, forecasting, structural inference, and policy analysis. The reduced form, recursive, and structural VAR, there are three broad types of VAR model: the reduced form, the recursive, and the structural VAR model. The reduced form for the VAR models consider each variable to be a function of its own past values, the past values of other variables in the model. And the recursive VAR model contains all the components of the reduced form model, but all allow some variables to be functions of other concurrent variables by imposing this short-run relationship. The recursive model allows us to model structural shocks. Structural VAR model includes restrictions that allow us to identify causal relationship beyond those that can be identified with reduced form of recursive models. And this causal relationship can be used to model and forecast impacts of individual shocks, such as policy decisions. While reduced form models are the simplest of the VAR models, they do disadvantages. Variables are not related to one another. The error term will be correlated across equations, and the means we cannot consider with impact individual shocks will have one on the system. If you are going to ask what makes up VAR model, a VAR model is made up of a system of equations that represents the relationship between multiple variables. When referring to VAR models, we often use special language to specify how many endogenous variables there are included, how many autoregressive terms are included. For example, if we have two endogenous variables and autoregressive terms, we say the model is bivariate VAR. Two model, if we have three endogenous variable and four autoregressive terms, we say the model is trivariate VAR model. In general, a VAR model is composed of n equations representing n endogenous variables and includes p logs of the variables. Specification: what is the appropriate log length in the VAR? There are three criteria, as I mentioned to the Akeike information criteria, Schwarz info criteria, and Hannah-Quinn criterion. All functions of M, so-called matrices T, the test statistic, and the variance covariance matrix, in practice fix an upper bound of log length, let's say 12, choose the Q, which minimize one of the information criteria. Akeike info criteria is consistent, let's say, for T more than 20. Schwarz info criteria and Hannah-Quinn criteria will always choose smaller models than Akeike info criteria. When we are going to perform this, you will understand this better on the EU, because we have to do for every variable singular estimation to being able to determine which model is going to be better fitted, and the log selection will be then estimated for the model. Estimation. Multivariate generalized least square estimates are the same as equation by equation OLS estimates, ordinary least squares methods. For unrestricted VAR model, maximum likelihood estimates and equation by the equation OLS estimates coincide. And when a VAR is estimated under some restrictions, maximum likelihood estimates are different from OLS estimations. Maximum likelihood estimates are consistent and efficient if the restrictions are true. The presentation of the results, it is rare to report estimates by coefficients. Instead, impulse response and variance decomposition will be used for this, and historical decomposition is also the part of the one specific shock. How will the variable evolve is going to be questioned and interpreted and answered. How do we decide what endogenous variable to include in our VAR model. From an estimation standpoint, it is important to be deliberate about how many variables we include in our model, in our VAR model. Adding additional variables increase the number of coefficients to be estimated for each equation and each number of logs. Introduce additional estimation error. Deciding what variables to include in VAR model should be founded in theory as much as possible. We can use additional tools like Granger causality or Sims causality to test the forecasting relevance of the variables. The unrestricted model, of course, is the assessment of the selection of the optimal log length in a VAR, evaluate the use of the impulse response function with a VAR, and assess the importance of the variation on the standard VAR, and critical appraise the use of the VAR with financial models, and the assess the use of the vector error correction model is going to be questioned if it is necessary. What is vector autoregressive model? The vector autoregressive model is a workhouse multivariate time series model that relates current observations of a variable with past observations of itself and past observation of other variables in the system. VAR models differ from univariate autoregressive models because they allow feedback to occur between the variables in this model. For example, we could use a VAR model to show how real GDP is a function of the policy rate and how policy rate is in turn a function of the real GDP. This is vice versa. The bilateral impact or relationship or the causality or correlation is going to be questioned. The advantages of the VAR model, a systematic but flexible approach for capturing complex real-world behavior, better forecasting performances is possible, and ability to capture the intertwined dynamic of time series data is subjected. VAR model is a multi-step process, and a complex VAR analysis involves specifying and estimating the VAR model, using inference to check and revise the model, and forecasting and structural analysis, as I mentioned to you in the former slides. How do we choose the number of logs in a VAR model? Log selection is one of the important aspects of VAR model specification. In practical application, we generally choose the maximum number of logs and the P maximum and evaluate the performance of the model, including to 1 to maximum. The optimal model is then the model VAR, vector autoregressive, which minimize some log selection criteria. These methods are usually built into software, and log selection is almost completely automated now, as in the EU we are doing. Estimating and inference in VAR models. Despite their seeming complexities, VAR models are quite easy to estimate. The equation can be estimated using ordinary least squares method. Given a few assumptions, the error term has a conditional mean of 0. The variables in the model are stationary. The large outliers are unlikely, and no perfect multicollinearity is expected. Under these assumptions, the ordinary least square estimates will be the consistent. The evaluated using traditional t-statistic and p-values is going to be subjected and questioned, can be used to jointly test restrictions across multiple equations. Forecasting. One of the most important functions of VAR model is to generate forecasts. Forecasts are generated for VAR model using forecasting algorithm. Estimate the VAR model using OLS for each equation. Compute the 1 period ahead forecast for all variables. Compute the 2 period ahead forecast using the 1 period ahead forecast, and iterate until the n variables, so each step ahead forecasts are computed. This is supposed to be the periods that you have as in the time series. Each time series has the periods, and you are going to estimate, and you go to the second period. Therefore, it is somehow not necessarily used. Reporting and evaluating the VAR models. Often, we are more interested in the dynamics that are predicted by our variable models than the actual coefficients that are estimated. For this reason, it is most common that VAR studies report the Granger causality statistics, impulse response functions, and forecast error decomposition. Log length in VAR. When estimating VAR or conducting Granger causality test, the test can be sensitive to the lag length of the VAR. Sometimes the lag length corresponds to the data, such as quarterly data has 4 lags, monthly data has 12 lags, etc. A more rigorous way to determine the optimal lag length is to use the Akaike info criteria or Schwarz-Bayesian info criteria. However, the estimations tend to be sensitive to the presence of the autocorrelation. In this case, following the use of information criteria, if there is any evidence of autocorrelation, further lags are added above the number indicated by the information criteria until the autocorrelation is removed. Usually you are getting the smallest criteria numbers, estimated variables, then you prefer to employ these lags for the model, because otherwise then you will not be able to perform your model and there will be misleading information. Information criteria, the main information criteria and the Schwarz and Bayesian criteria and the Akaike criteria, they operate on the basis that there are two competing factors from adding more lags to the model. More lags will reduce the regression analysis, but also means a loss of the degree of freedom, which is also very important for estimating the model. Penalty from adding more lags. The aim is to minimize the information criteria by adding an extra lag. It will only benefit the model if the reduction in the regression outweighs the loss of degree of freedom. In generally, the Schwarz-Bayesian info criteria has a harsher penalty term than the Akaike info criteria, which leads it to indicate the parsimonious model is the best. The Akaike info criteria and Schwarz info criteria is represented in the below equation as it is given. The logarithm and ln is given, and the sigma represents the residual, and the t is the sample size, and k is the number of parameters. As you are observing, the Schwarz Bayesian criteria and Akaike info criteria is a little bit different, but it is helping hand for estimating the best lag representation for the model. The multivariate information criteria, the multivariate variation of the Akaike information criteria is similar to the univariate, as it is given here, the log variance, which is given for the summation or the sigma. The covariance matrix of the residual is represented with the sigma or the summation. This gives the variance on the main diagonal and covariance as between the residual of the main diagonal of the matrix, and t, as I mentioned, t is the number of the observations, and k is the total number of the regressors in all equations is given in the model. The multivariate version of the Schwarz-Bayesian info criteria is then again given here as it is represented. I have already explained. The best criterion here, then there is no agreement on which criteria is best, but as I mentioned to Akaike info is usually preferred, and Schwarz-Bayesian is also used. In generally, there is no agreement on which criteria is fitted to the model. The Schwarz-Bayesian is strongly consistent but not efficient, as it is written here, and the Akaike is not consistent also, generally produce too large models but is more efficient than the Schwarz-Bayesian. As I mentioned to you, I myself use always Akaike info for determining the lag structure, let's say which lag will be used. Criticism of causality test. Granger causal test much used in VAR modeling, however, do not explain some aspects of the VAR. It does not give the, because you know the causality test is only give the relationship and the causality and correlation between the variables, and this is not the good information about the model. It just only gives you how it is affecting, whether it is affecting or not affecting the bilateral or bidirectional affect or relationship or causality will be then estimated. It does not give the sign of the effect. We do not have if it is positive or negative. It does not show how long the effect lasts for, and it does not provide evidence of whether this effect is direct or indirect. In general, the VAR has all the log length of the individual equations the same size when we are going to question the unrelated regression. It is possible, however, to have different log length for different equations. However, this involves another estimation method. When log length differs, the seemingly unrelated regression, so-called the SU approach, can be used to estimate the equations. This is often termed as the NIAVA. An alternative VAR, it is possible to include contemporaneous term in a VAR. However, in this case, the VAR is not identified. It is also possible to include exogenous variable in the VAR, although they do not have separate equations where they act as a dependent variable. They simply act as extra explanatory variables for all the equations in the VAR, and it is worth noting that the impulse response functions can also produce confidence interval to determine whether they are significant. This is routinely done by most computer programs. The vector error correction that we have done last lecture are the basic VAR with an error correction term incorporated into the model. The reason for the error correction term is the same as with the standard error correction model. It measures any movement away from the long-run equilibrium. These are often used as a part of the multivariate test for the co-integration, such as the Johansen maximum likelihood test. The vacuum, however, there are a number of differing approaches to modeling vacuums. For instance, how many logs should there be on the error correction terms? Usually just one, regardless of the order of the VAR. The error correction terms becomes more difficult to interpret as it is not obvious which variable it affects following shock. The Wald test statistic explains the short-run causality that we are not using between variables, while the statistics provided by the logged error correction terms explain the intensity of the long-run causality effects, and short-run range causalities are determined by the Wald statistics for the significance of the coefficients of the series. And criticism for the VAR: many argue that the VAR approach is lacking in theory. There is much debate on how the log length should be determined. It is possible to end up with a model including numerous explanatory variables with different signs, which has implications for degree of freedom, and many of the parameters will be insignificant. This affects the efficiency of regression. There is always the potential for multicollinearity with many logs of the same variable, and stationarity and the VAR. When we are going to question, should a VAR include only stationary variables to be valid? Sims argue that even if the variables are not stationary, they should not be first difference. However, others argue that a better approach is multivariate test for co-integration and then use first difference variables and the error correction term. The VAR example, when we are going to give the simplest understanding here, the basic T behind this following model is simply that, the T-bills, it should be there. We believe there is a relationship between short-term T-bills and the long-term R10 interest, which is the interest rates. It is wrong written, theory should be written. We believe the VAR approach is the best model in this case. Following the Akaike and Schwarz-Bayesian criteria, we find the VAR of order 1 is most appropriate. This produced the following results, which is not estimated currently. It is only taken from the model. The OLS estimation is given here. As you see, the probability values and the T statistics is going to be evaluated, and if it is smaller, then you are going to perform. If it is larger, then you are going to question again, looking to the Akaike info criteria and Schwarz-Bayesian all, and determine to perform the VAR model whether it is sufficiently supporting your estimation or not. The Granger causality statistics, as we previously discussed, the Granger causality statistic tests whether one variable is statistically significant when predicting another variable. The Granger causality statistics are the F statistic that tests if the coefficients of all logs of a variable are jointly equal to 0 in the equation for another variable, as the p-value of the F statistic decreases, evidence that a variable is relevant for predict another variable increases. The Granger causality tests whether a variable is helpful for forecasting the behavior of another variable is then estimated. It's important to note the Granger causality only allows us to make inference about forecasting capabilities, not about true causality. The Granger causality statistic, as we previously discussed, Granger causality statistic tests whether one variable is statistically significant when predicting another variable. The Granger causality tests are the F statistic. The test if the coefficients of all logs of a variable are jointly equal to a 0 in the equation of another variable. As p-value and the F statistic decrease, evidence that a variable is relevant to predict another variable. As I mentioned to you, this is double repeated. The Granger causality test is given also here. As I mentioned, we are going to look the probability value again. If it is less than or higher, then you determine whether it is related to each other or not, whether there is correlated or not, there is any relationship between each other or not. In an example, I give you here again the Granger causal test for x to y. If the p-value is 0.02, we would say that x does not help predict y at the 5% level. However, if the p-value is 0.3, we will say there is no evidence that x helps predict y. Granger causal test continuing again with the theoretical information. According to Granger causality, can be further subdivided into long run and short run causalities. This requires the use of error correction models or the vector error correction, depending on the approaches for determining causality. The long run causality is determined by the error correction terms, where if it is significant, then it indicates evidence of the long run causality from the explanatory variables to the dependent variable. And short run causality is, and this is of course for the vector error correction, causality is determined as before with a test on the joint significance of the lagged explanatory variables using an F test or VAR test. Impulse response and variance decomposition. The impulse response, as I have explained in the last lecture, are the relevant tools for interpreting the relationship between the variables, and variance decomposition examine how important each of the shocks is a component of the variables, so-called the unpredictable variance of each of the variables over time. The impulse response function traces a dynamic path of variable in the system to shock to other variable in the system. This is done by estimating the VAR model, implementing a 1 unit increase in the error of one of the variable in the model, while holding the other errors equal to 0. Predict the impact of H period ahead of the error shocks, or the M period, so-called the last one. Plotting the forecasting impacts along with the one standard deviation confidence intervals. The impulse response function is given below, as it is given in the matrix. Also, it can be used, or you can use in the equation. And this is then the shocks which is estimated by using this impulse response. I have here another example I will give you. The impulse response also trace out the effect on the dependent variable in the VAR to shock to all the variables in the VAR. Therefore, in a system of two variables, there are 4 impulse response functions, and with 3, there are 9 regarding to this estimation. The shock occurs through the error term and affects the dependent variable over time. In effect, the VAR, or so-called the vector autoregressive, is expressed as a vector moving average model. As the univariate case previously, the shocks to the error terms can then be traced with regard to their impact on the dependent variable. If the time part of the impulse response function becomes 0 over time, the system of equation is stable. However, they can explode if unstable. The impulse response function traces the dynamic part of the variables in the system to shock to other variables in the system. This is done by the estimating the VAR model, implementing a 1 unit increase in the error of one of the variable in the model, while holding the other errors equation to 0, and predicting the impact of the H period ahead to the error shocks, and plotting the forecasting impact along with the one standard deviation confidence intervals. The impulse response sample is interpreted here. As you see, the results on the I have given you the last lecture also similar example. The results show here the impulse response to dependent variable. Only here, as I mentioned, the nominal interest rate is represented and illustrated on the table. And as you see, as much as the negative and the positive signs indicates the impact to the dependent variable, and as positive response to the, as nominal interest rate has positive response to the consumer price index, but the all other variables, as you see, there are some negative signs, and this is then the indication that there is a negative relationship and impact to the consumer price index. The impulse response positive values have positive negative values, have negative effects on the dependent, as it is represented on the graph. The variance decomposition estimate and interpretation is also given here. And here then the real GDP is given for the consumer price index and the real effective exchange rate, nominal interest rate again. And when you are looking to the numbers, the higher the values, it becomes then the affection of the explanatory variables on the dependent variable. Therefore, here, when you are looking to the numbers, you are observing the real GDP becomes more higher than the others, and also comparing to the others. The CPI are not taken because CPI, each other is not important because it's here. It is higher here, but it's not necessary to consider. The real effective exchange rate is also higher, but nominal interest rate for the variance decomposition is very low. Therefore, we are considering only the real GDP value supposed to be more highly affected regarding to the others, and also real effective exchange rate is also becoming higher compared to the nominal interest rate and affects the consumer price index. The inflation to inflation is also represented here. As you see, positive values becoming the positive relations and negative then negative. As you see, inflation to inflation, then the relationship is represented on the left, and on the right, output to inflation is represented, and there is mostly the negative values. And as I mentioned to you, it is better for observing the positive values affecting each other. Long-run causality before the error correction model can be formed. The first has to be evidence of cointegration, given the cointegration implies a significant error correction theorem. Cointegration can be viewed as an indirect test of long-run causality. It is possible to have evidence of long-run causality, but not short-run causality, and vice versa can be accepted. In multivariate causality test, the testing of long-run causality between two variables is more problematic, as it is impossible to tell which explanatory variable is causing the causality through the error correction term. The symbol is given here. As an example, let's consider VAR with three endogenous variables: the unemployment rate, the inflation rate, and the interest rate. To estimate the structural VAR model of this system, we have to put restrictions on our model. For example, we may assume that the FED, the so-called the Central Bank of America, follows the inflation targeting rule for setting interest rate to a certain limit, and this is assumption would be then build the model regarding to this regulation, and our system, then the equation will be then estimated after this policy and the measures. The specification, what is the appropriate log length in the VAR? There are, as I mentioned to you, three criterion: Akaike, Schwartz, and Hanna. And in practice, is fixed an upper bound of the log length is usually 12, 1 or 2. Choose the Q, which minimize one of the information criteria, and Akaike info Schwartz is the inconsistent, which is more than 20. If the T value is more than 20, the Schwartz info criteria and the Hanna Queen criteria will always choose smaller model, and then models than the Akaike info criteria. And the estimation multivariate generalized least squares estimates are then the same as equation by the equation of OLS estimates. For unrestricted VAR model, multivariate linear model estimates, and equation by the equation OLS estimates. And when a VAR is estimated under the some restrictions, the multivariate variate linear model estimates are different from the OLS, and multivariate estimates are consistent and efficient if the restrictions are true. It is the area to respond to the estimated VAR coefficient, the impulse response, and the variance decomposition will very helpful for interpreting and explaining, and the relative contribution of the different shocks to the fluctuation on the variable will be then interpret. And historical decomposition also used given the path of one specific shock to determine the variables, let's say, during the period of time, improvement or changing. How do we decide what endogenous variable to include in our VAR model? From an estimation standpoint, it is important to deliberate about how many variables we include in our VAR model. Adding additional variables increase the number of coefficients to be estimated for each equation, and each number of lags introduce additional estimation error. Deciding what variable to include in your vector autoregressive model should be founded in theory as much as possible, and we can use additional tool like range causality or SIMS, as I mentioned to you, to test the forecasting relevance of variables. The estimation and the inference in the VAR models, despite their seeming complexities, VAR models are very easy to determine and estimate if you follow the guideline. The equation can be estimated using ordinary least square given in a few assumptions. The error term has a conditional mean of 0. The variable in the model are stationary, and large outliers are unlikely, not desired. An outlier I am mentioning of the here will be then interesting to give you the information about it. Is an unusually large or small observation is the outlier. Outliers can have a disproportionate effect on the statistical results. Therefore, such things that happen in the model must be carefully treated. And when you are going to observe, then the mean, which is very important also for estimating, then can results is then becomes a misleading interpretation for you, let's say, estimation calculations. And no perfect multicollinearity is also expected. Under these assumptions, the ordinary least square estimates then is expected to be consistent, can be evaluated using traditional t-testing and p-value, as I am always doing, and can be used the jointly test restrictions across multiple equations. And one of the most important functions of the VAR model is to generate forecast VAR model using the iterative forecasting algorithm, estimating the VAR model using the OLS for each equation, computing the 1 period ahead forecast for all variables, computing the 2 period ahead forecast like time series for 1 period of time, as I mentioned to you, using the 1 period ahead forecast, iterate until the n period or each step ahead forecast are computed regarding to this. Reporting and evaluating the VAR model. Often we are more interested in the dynamics that are predicted by our VAR models than the actual coefficients that are estimated. For this reason, it is most common that VAR studies report the range causality, impulse response, and forecasting error decomposition. The forecasting error decomposition separates the forecast error variance into proportion attributed to each variable in the model. Intuitively, this measure helps us judging how much of an impact one variable has another variable in the VAR model and how intervened of our variables dynamics are. And for example, if X is responsible for 85% of the forecast error variance of Y, it is explaining a large amount of the forecast variation in X. However, if X is only responsible for 20% of the forecast error variance of Y, much of the forecast error variance of Y is left unexplained by X. And if we are going to ask what is the difference between the VAR and vacuum model, through vacuum we can interpret the long-term and short-term equations. We need to determine the number of co-integrating relationship. The advantage of the vacuum over VAR is the resulting VAR from vacuum representation has more efficient coefficient estimates when to use VAR or vacuum. You should use vacuum if your variables are non-stationary and you find the common trend between the variables co-integration. And why is VAR better than autoregressive? VAR, so-called vector autoregressive regression, is a generalization of the autoregressive model for multiple time series, identifying the linear relation between the variables. The autoregressive model can be seen as a particular case of the VAR for only one series. And the conclusion, as a concluding remark, we may then say VAR model are an essential component of multivariate time series modeling. You should have a better understanding of the fundamentals of the VAR model, including what is, as I started in the beginning, what our VAR model is, who use VAR model, basic types of the VAR models, how to specify VAR model, and estimation and forecasting with the VAR model. And VAR have a number of important uses, particularly causality tests and forecasting, to assess the effects of any shock to the system. We need to use impulse response function and the variance decomposition. Vector error corrections are an alternative as they allow first differencing variables and an error correction theorem. The VAR has a number of weaknesses. Most important, its lack of theoretical foundations. This was the presentation for today. If you have any question, you may ask me. If not, then I will stop here. Do you have any question?
No, sir.
I will upload this again to the system and to YouTube, then you can watch again. The guideline will be then introduced to you. And next week, as I said to you, I will give you the quantitative regression with comparison to the OLS, and then finish this semester. After then, I will give you one more assignment, or you will do one more application after the Sylvester. You will do any of this method or tests with your own data, then I will evaluate you to the final exam. Okay. Okay then. Thank you very much for your joining.
Thank you, sir. Good night.
Thank you. Thank you, John. Bye-bye.